Hello everyone, welcome. My name is Ahmad and I'm absolutely thrilled to be your instructor today. Before we dive into the exciting world of multi-agent architectures, I have a quick but important disclaimer. The medical diagnostics scenario we're exploring today is purely a conceptual, educational example designed to showcase our framework's reasoning capabilities. It is not real medical advice and shouldn't replace professional clinical judgment. Now, today we are diving into Octochains, a fantastic lightweight zero-dependency Python framework designed for complex problem solving. You see, standard AI workflows usually rely on a single prompt or a sequential chain of agents. While that works for simple tasks, it often leads to what we call cognitive tunnel vision. This is where a model commits to a logical path way too early and completely ignores alternative perspectives. Here's where things get interesting. Octochains solves this by using a MapReduce-inspired architecture called parallel isolated reasoning. In simple terms, what this means is we first map the problem by broadcasting it to multiple specialized agents simultaneously, each working in a completely private, isolated thread so they don't bias each other. Then we reduce by using an official synthesizer to collect those independent reports and merge them into one unified high-confidence consensus. Pretty neat, right? So why exactly are we using Octochains? It all comes down to the power of decomposable tasks. These are highly complex, multifaceted problems that can be logically broken down into distinct, independent domains of expertise. Instead of asking one generalist AI to solve everything, which, let's be honest, usually leads to hallucinated logic or shallow analysis, I'll assign each sub-problem to a dedicated expert. Think about medical diagnostics, where we look at a patient through the lens of cardiology, psychology, and pulmonology all at once. Or enterprise due diligence, separating financial risk from legal compliance. Because Octochains enforces strict isolation, these experts evaluate their specific domains without ever influencing each other. This completely eliminates groupthink and guarantees that crucial domain-specific insights aren't lost in the noise before the aggregator makes the final decision. Now that we understand the theory, let's get our hands dirty. Before we can write any code, we need to set up our environment. First, we need to install our core dependencies: Octochains for orchestration, OpenAI to access our language models, and Python.env to manage our API keys securely. Let's run this installation to get started. With our packages installed, let's set up our environment. In this step, we're going to import the core modules we need, like the Octochains engine, the agent base class, and our synthesizer aggregator. We'll also securely load our OpenAI API key using .env. Having a clean environment set up ensures our agents can communicate with the language model smoothly without any credential hiccups. Let's run this cell to get everything loaded up. Let's start by importing our necessary modules. We'll need OS and .env to handle our API keys, chat OpenAI as our language model. And from Octochains, we pull in the core agent and engine classes, along with the synthesizer aggregator to merge our results later. Now, let's add a quick comment here to remind us that we are loading our API keys securely from our environment. We call load.env here to read our local.env file and load those environment variables into memory. And finally, we'll set our OpenAI API key environment variable, falling back to a placeholder if it's not found in the environment. Let's run this to get our workspace ready. Now, here's where things get interesting. Octochains is what we call a pure engine. In simple terms, what this means is that Octochains doesn't force you to use a specific LLM provider. It handles the orchestration, but you bring the brain. To do that, we need to define a universal model-agnostic callable function. This function, which we'll call OpenAI LLM callable, it takes a prompt, sends it to OpenAI's GPT-4o, and returns the text. This standardizes how all our agents will talk to the AI. Let's write that function now. Since Octochains is model agnostic, we need to define a universal LLM callable function. We are calling this function OpenAI LM callable because it takes a raw prompt string, instantiates our chat OpenAI model with a temperature of 0 for consistent reasoning, invokes it, and returns the raw string content. Let's see if this compiles successfully. With our LLM connection ready, it's time for step 2, creating our specialists. Remember, the magic of Octochains lies in parallel, isolated reasoning. We want our agents to analyze the patient data independently without biasing each other. To do this, we'll create custom classes that inherit from the base agent class. Let's start with our first specialist, the cardiologist. We'll define their specific role, their goal, and their unique prompt. This ensures they focus strictly on cardiovascular health and nothing else. Let's create our first specialized agent. We'll define a cardiologist class that inherits from the base agent. In the constructor, we call super init raise to set its role, define its specific clinical goal, describe the input it expects, and pass in our newly created OpenAI LLM callable. Next, we implement the execute method. This is where the magic happens. We construct a highly focused prompt instructing the LLM to act specifically as a cardiologist, inject the patient's medical report, and run it through our LLM callable to return isolated specialist insights. Now let's look at why this matters. If we only had a cardiologist, we'd miss the bigger picture. That's why our second specialist is the psychologist. This agent is going to look at the exact same patient data, but through a completely different disciplinary lens, focusing on mental health, anxiety, and cognitive symptoms. Because Octochains runs these agents in isolated threads, the psychologist won't be influenced by the cardiologist's findings. Let's define this agent next. Now, let's define our second specialist, the psychologist, by subclassing our agent base class and specifying its unique role, goal, and our LLM callable. Next, we implement the execute method where we construct a tailored prompt focusing strictly on mental health and return the LLM's assessment. Here's where things get interesting. We have our heart and mind experts ready, but we need one more specialist to look at the respiratory side of things. Let's define our third agent, the pulmonologist. This agent is going to focus entirely on respiratory health, looking for signs of asthma, COPD, or infections. By keeping this pulmonology analysis in its own isolated thread, we ensure it won't be biased by what the cardiologist or psychologist might find. Let's write the code for it. All right, let's build our third specialist, the pulmonologist, setting its goal to target respiratory and lung-related conditions. And just like before, we define the execute method to construct a prompt that forces the LLM to act as a pulmonologist and evaluate the report. Now, let's look at why this matters. We have our three specialists defined, but they need some data to analyze. In this step, we're going to prepare our patient data. We'll create a mock patient profile for David Wilson, a 68-year-old male presenting with a mix of symptoms: shortness of breath, chest tightness, anxiety, and forgetfulness. This single block of text is what we will broadcast to all three of our agents simultaneously. Each of them will analyze this exact same data from their own unique perspective, completely in parallel. Let's create a new variable here to store our mock patient data, which contains a mix of cardiac, psychological, and pulmonary symptoms. If we run this print statement, we'll see the structured clinical notes we're going to feed into our parallel reasoning engine. In simple terms, what this means is we now have our experts and our patient data, but we need someone to bring it all together. This is where the synthesizer aggregator comes in. Think of it as the chief integration officer. It's going to take those 3 isolated independent reports and merge them into a single cohesive clinical narrative. We'll initialize our 3 agents, set up our synthesizer with a custom goal to find exactly 3 key health issues, and then bundle them all into the Octochains engine. Let's write the setup code. Now we're ready to set up our pipeline. Let's start by adding a comment to keep our code clean and organized. We'll instantiate our Cardiologist agent first. Next, let's spin up our Psychologist agent. And we'll do the same for our Pulmonologist agent. Now, let's add a comment indicating we're setting up the aggregator. We are calling the synthesizer class here, passing in our LLM callable and a custom goal to merge these 3 perspectives into exactly 3 core issues. Let's close the parenthesis for our synthesizer initialization. We'll write a quick comment to mark the creation of our orchestrator engine. Finally, let's build this. We construct our engine by passing in our list of isolated agents and our team lead aggregator. Now let's put everything into action. When we call engine.run, the Octochains engine does something beautiful. It broadcasts our patient data to all 3 specialists at the exact same time. It spins up parallel, isolated threads, waits for them to finish their work, and then hands those independent reports over to our synthesizer. By setting show log to true, we'll be able to watch this orchestration happen in real time right in the console. Let's run the pipeline and see it in action. All right, let's execute this. We are calling the engine's run function here because we want to kick off the parallel reasoning process on our patient data. Setting show log to true will let us see the live execution logs of our agents as they run in isolation. Let's see what this outputs. So as you can see, during phase 1, the engine dispatches 3 separate parallel threads. 1 for the cardiologist, 1 for the psychologist, and 1 for the pulmonologist. Notice how they are launched simultaneously. They are analyzing the exact same patient data, but doing so in complete isolation to prevent any logical contamination or groupthink. As each parallel thread finishes, the engine successfully collects their independent structured reports. Then we move to phase 2. The engine takes those 3 pristine, unpolluted perspectives and pipes them directly into our aggregator, the chief integration synthesizer. This aggregator will evaluate the contrasting insights and generate our final balanced diagnostic consensus. Now that our engine has run, let's move on to step 4, where we format the final consensus. Because we utilized Octochains' built-in synthesizer, we don't just get a wall of unstructured text. Instead, we receive a beautifully structured object complete with a narrative, key clinical takeaways, and a programmatic confidence score. Here's where things get interesting. When we run the next code cell, we'll see this data cleanly printed out as an executive summary, followed by the key takeaways and the metadata. Let's execute the code and see what our expert panel concluded. Let's create a new variable here to store our final consensus results extracted directly from the report. We'll print a nice divider line to separate our output visually and make it highly readable. Let's print a bold clear header for our final multidisciplinary diagnostic report. We'll close the header block with another divider line to keep things clean. Now we check if our consensus data has a narrative attribute, and if so, we'll print the executive summary section. Next, let's loop through the key clinical takeaways generated by the synthesizer and print them out as a numbered list. We'll also print out the report metadata showing the calculated confidence score formatted beautifully as a percentage. Finally, we'll add a fallback else block to print the raw consensus data if our structured attributes aren't present. Let's run this and see our final diagnostic output. Now, let's look at why this matters, specifically focusing on that confidence score. The synthesizer doesn't just blindly copy and paste the reports together. It actually evaluates the alignment between them to calculate a programmatic confidence score from 0 to 100%. In simple terms, what this means is that if our cardiologist, psychologist, and pulmonologist all point toward overlapping or complementary issues, the score stays high. But if they wildly contradict each other, the score drops. This acts as a powerful quality gate for enterprise applications, giving you a mathematical measure of agreement before you take action. Now, as you can see, we have the final diagnosis. Notice how the synthesizer blended the isolated insights from all three specialists. The summary accurately captures the overlapping cardiac, respiratory, and cognitive issues as a unified whole. As you can see, we have an 85% confidence score at the bottom. The synthesizer doesn't just blindly copy and paste the reports together. It actually evaluates the alignment between them to calculate a programmatic confidence score from 0 to 100%. In simple terms, what this means is that if our cardiologist, psychologist, and pulmonologist all point toward overlapping or complementary issues, the score stays high. But if they wildly contradict each other, the score drops. This acts as a powerful quality gate for enterprise applications, giving you a mathematical measure of agreement before you take action. And there you have it. You've successfully built a contamination-free, multi-agent reasoning pipeline using Octochains. I hope this gives you a clear picture of how parallel isolated reasoning can prevent cognitive bias in your AI workflows. If you found this tutorial valuable, please subscribe to the channel for more advanced AI engineering guides. And if you're enjoying the framework, please head over to GitHub and start the Octochains repository. It really helps support the open source project. Thank you so much for watching. I'm Ahmad, and I'll see you in the next one.